We know that the relationship between delta t and delta t prime is this. Let's see. We know that delta t is equal to delta t, the proper time, divided by this value. And we've defined what the proper time is, and we've worked all that out. We said that if two events occur at the same point in space in a reference frame, that is what we call the proper time, or the delta big T. So in which case here is going to be the proper time, or is going to record the proper time. Well, the two events we're looking at are where the ship goes past the sun, that's event 1, and the second event where the ship goes past Jupiter, it's event 2. Now in the rocket's reference frame, we'll start with this one. In the stationary observer reference frame, this event occurs at this point in space, and the rocket moves, and then the second event occurs at this point in space. So these two events occur at different points in space. Therefore, this one can't record the proper time, because we've defined what the proper time is. But in this case, the first event of the sun passing occurs at this point, and then after a while, after delta t prime, this Jupiter is going to pass and also pass this point at the same point in space. So the two events of the sun passing and Jupiter passing, since we're referring to the rocket in a stationary reference frame, are both going to occur at the same point in space. Therefore, it's this reference frame that's recorded that is recording the proper time. Alright, so now we know what the relationship is between delta t and the proper time, and we know which reference frame is recording the proper time. So the time interval delta t is going to be what we measure according to this reference frame, the time, and the big T is going to be what we reference towards this reference frame time. So we can write that in a relationship. Let's get rid of some room. Like always, I've always run out of room. I'll rewrite this. Okay. So we know that L over delta T is equal to L prime over delta T prime. And we know that delta T is equal to this, where in this case, this delta T prime is our proper time, so that should be equal to delta T over our proper time. And since we know, if we were to rearrange this formula, we could say our proper time, if we multiply both sides by this value, we would get a proper time is equal to delta T times our 1 minus V over C squared. So we can substitute this value for our proper time into this formula, and we'd get L prime over, we'd get delta T times this value, or we'd simply get L over delta T is equal to L prime over delta T times this value, 1 minus V over C squared. Now we can multiply both sides by delta T. Now we could do delta T here and delta T here, and these two are going to cancel, and these two are going to cancel. And we're simply going to left with this formula here, that our L value, or our length that we record in this reference frame, is equal to the length we record in this reference frame divided by this value, which is dependent on the velocity that you're traveling. So here you get a relationship for the two lengths, for the two reference frames. We get that L is equal to L prime divided by the square root of 1 minus V over C squared. So this gives a relationship just like our equation for our time dilation. This gives our equation for our length contraction. Because the lengths are going to be different for different reference frames. So one reference frame is going to have a length shorter than the other. So we see that L prime does not equal L. So the distance between two objects in reference frame S prime is not the same as the distance between two objects in the reference frame of the rocket, or S in the rocket. Now, because in reference frame, which reference frame are we talking about? In reference frame S, the two objects whose distance length we are measuring are stationary. That is, in reference frame S, these two objects which we're moving, we're measuring the rocket passing past these two objects, and we're measuring the length between these two objects. These two objects which we're measuring the length of are stationary, while in this one we're measuring this length, but these objects are moving. Now, in the reference frame where the objects you're measuring are stationary, we call that the proper length. So this measures the proper length. So we give a definition of the proper length just like we give the definition of the proper time. And we can write the equation like this, where delta L is equal to the square root 1 minus V over C squared times L, where this L value is the proper time, and it's recorded in the reference frame where the things being measured are stationary. Hope that makes sense. So you can see that this value of L prime is going to be less than L, because whatever velocity we have here, we're going to get a value that is less than 1. So this value here is always going to be less than 1. Therefore, we're timesing L by a value less than 1, so we're going to get a value that's less than L. And so L prime is always going to be less than L, unless the velocity is 0. So the length measured in the reference frame L, or the reference frame with a proper time, is always going to be greater than the length measured in the reference frame that is moving, where the things that you're measuring are moving. So the length is going to contract or get smaller in those reference frames compared to the other reference frames. So that's what we call length contraction. So as you move relative to the length of an object, that object shrinks in length. So our idea of absolute length or absolute time have both been thrown out the window, and we've shown here that for this to be reconciled, we need the length of the reference frame moving to be equal to this value times the length of the reference frame stationary. And so there you go.